Hello, I've speeded up a bit the intro because we don't have 2 hours in front of us, and maybe this little sound distortion will prevent a ban from YouTube copyright bots. Who knows? I'm Teuwen, Doegox on the internet. I'm a team leader of the cryptography and embedded security team at Quartz, and you may have heard about me from various topics mixing hardware and software, like grey-box attacks against white box crypto, tier-off attacks against EEPROM, such as in RFID and NFC tags, attacks on the Titan M with some chip-off and micro-soldering. I'm also in the NFC and the Proxmark project. I organize hardware-oriented CTFs, and I'm in the editorial team of the Poco GTFO. If you don't know it yet, I encourage you strongly to have a look at it later. So what's a WooKey? It's a secure USB mass storage developed by the NC. On the left, you see a prototype of the concept. On the right, a development board with its components. So it's use an encrypted SD card for the storage, and there is a touchscreen with, as you can see, a randomized keyboard layout at each booted change. And there is also a slot for a smart card, a JavaCard, where the keys needed to decrypt the storage are held. So how to use it? You plug it to your PC in USB, you insert the authentication token, you type in a first pin, which is called the pet pin. If it's correct, the WooKey will display its little pet name, and then you can type the real pin to decrypt the SD card, and a mass storage will appear on your machine. The first phase with the pet pin and pet name, it allows you to detect an attempt of phishing with a fake WooKey. For example, if the WooKey you have in hand cannot show you the expected pet name, beware, maybe someone is trying to steal your user pin and decrypt your stolen WooKey. A bit of context on why I'm talking about a few hardware hacks on the WooKey. With the ANSI in France, which is the National Cybersecurity Agency, it delivers certifications to products, which are called CSPN. That's French for First Level Security Certification. And these certifications rely on security evaluations performed by private labs. They are called CESTI in French, Information Technology Security Evaluation Facility. Quartz is one of these CESTI. It's a software CESTI by opposition with the hardware CESTI. And the ANSI organize regularly so-called inter-CESTI challenges, typically on open source products, to check how these labs perform. And the last product to be audited was the WooKey. So it's an open source project developed by the ANSI itself. They designed both the hardware and the software, and they try to implement best security practice in all the layers of the product. So really a good defense in-depth approach. We set a quite large evaluation plan, and each CESTI received a part of it. So each CESTI looked at different portion of the product. And novelty for this inter-CESTI, the evaluation items and the skills were mixed. So the software CESTI had also to evaluate some hardware aspects and vice versa. Clearly, this talk is not much about the WooKey itself. This is labeled episode 7 for some reason. I'm aware of at least 4 previous talks on the WooKey, so you can easily find online more details on the internals and the layers of defense. And with episode 7, I have some margin. Now, what I want to show you is how you can mount hardware attacks yourself quite easily without expensive equipments. I've picked 3 topics to give you an overview. How to mount timing attack on a Java card or smart card. How to automate a pin brute force by hijacking a user interface, and how to set up an electromagnetic fault injection test bench at home. So let's go for the first example. The idea is to check if a pin validation doesn't leak anything in its response delay that would give us information useful to find the correct pin. Here I show you against a card used in the WooKey, but the same principle applies, for example, on passwords to unlock a microcontroller like an ECU secure session or on a locked GTAC port, etc. The idea is very simple. You send the pin or the password and you measure how much time it takes for the card to respond. If the pin is correct, the timing will probably be quite different, but that's fine. That's when you know the pin. The problem can occur if you get slightly different timings between a completely wrong pin and one with, for example, the first digit correct or the length correct. So for example, here, if it's a pin 1, 2, 3, 4, you measure the timing for 9999 and the timing for 1999. And maybe the timing of that one will be slightly longer than this one if, for example, the card is stupidly checking the digit one by one. Maybe it's reverse, so it's good to test also the end. And maybe the problem is on the length of the pin. So when you try the pin of a correct length, you will get a different result than when the length is incorrect. Spoiler alert, in the source code of the WooKey, we see they use the JavaCard API in their applet, so there is nothing really suspicious over there. But still, let's see how we can mount such attack. What do you need to mount it? A logic analyzer. A cheap one is okay because smart card is almost like a UART with a single line mixing RX and TX. You can see here the pinout. So you have one IO, which represents really what you get as RX and TX on a regular UART. And you need, of course, the ground to have a reference, and you write a little script to do trace acquisitions and to send commands on the smart card. You need to choose a target that accepts quite some pin attempts before killing itself. So here we modify the WooKey applet to be able to test mini pins without triggering the countermeasures that exist in the real applet of the WooKey. So how to hook on the smart card IO lines? Two possibilities. One is to pick the lines directly from the reader if you can open the reader and modify it. Here you see I added a small pin header to a commercial reader, and you see that we've got only 2 wires that go to the logic analyzer. The other possibility, if you cannot touch the reader, is to add an extension with a fake card and a fake reader. So here we have a fake card that goes to the WooKey, and here a cable that deports a fake reader just to be able to put the real card here. So we have no room somewhere here to get the IO and ground line that we need for the logic analyzer. Then you record a trace when you send a pin to the card, and you see it's quite straightforward. You have only one channel to monitor, and you see some activity, which is the command that you send, and then some activity, which is the response of the card. And the only thing we are interested in is the timing between the command and the response. And that's what we want to watch. So you get your measures. Here, for example, we test for the pin length. We set up first a pin of length 4 in this column, and here a pin of length 8 in this column, and then we try pins of different length with the wrong pins. Like we try to inject 9, then here 99, then here 999, etc. And you see when the correct pin is sent, the timing is very different. Now, do you see something else interesting here? Beside the correct pin, look at what are the longest timings in this list. And yeah, the longest timings are here and there. And when your pin is of length 4, that's when you try a pin of length 4. When the pin is of length 9, the longest timing is when you try a pin of length 9. Oops. So you see we got here timing dependency, and we can find the correct pin length. Hopefully, we tested it further. There is no dependency on the first or last digit being correct or not, so you don't have a full timing attack against the content of pin, but still, you can discover the correct pin length via this method. Actually, it's not a bug in the WooKey applet itself, and it's really in the JavaCard OS of the card we tested, which were, by the way, our own cards, as we were using a modified version of the WooKey applet. And we found that bug in the GCOP3 and GCOP4 cards, which are quite highly certified. One is AL5+, the other one is an AL6+. Again, no panic. Typically, the number of pin attempts should be very limited in most applications, but still it's an information leak that shouldn't be really there. And it was reported to the vendor. The second example is taking control on the user interface via the SPI bus to enable some brute force on the pin. But to explain that one, I have first to explain the cryptographic vulnerability in the WooKey protocol, because the pin is not supposed to be brute force, as there is a limit in the number of attempts. You remember I told about the pet pin and pet name, and here is how the first phase of the authentication protocol works. So from the pet pin, where is my pencil here? From the pet pin, the WooKey derives a decay by some derivation function, and the decay is sent to the token. Then the token, it has an encrypted key block called ELK internally, and it decrypts the ELK with the decay that you provide, and it gives a KPK, which is sent to the WooKey. And the KPK, if it's correct, it's used to decrypt a key store. And from there, it can mount a secure channel with a token, ask for the pet name to the token, and display the pet name to the user. So where is the vulnerability here? Well, actually, so you provide the decay to the card and you get the KPK back from the card. So you can compute yourself the ELK which is stored on the card, because you just need to reverse the decryption that we get here, and you can just re-encrypt the KPK that you got with the decay, and you obtain back the ELK. Okay, but that means you need the correct decay, which means you need the correct pet pin, so that's not really an issue, right? Well, actually, no, you don't need that even. Because if you provide a wrong decay, the card will happily compute a wrong KPK and return it. So you can re-encrypt the wrong KPK with the wrong decay, and you get back the real ELK again. So you can extract the ELK from the token just like that without knowing any pet pin. What can you do with that? Once you get the ELK, the idea is to create a fake card for the WooKey where we could disable the countermeasures present in the real token. I told you the token limits the number of pins you can try, and it has even an additional countermeasure where there is an increasing delay every time you try a wrong pin. This is the type of countermeasure, for example, you have in some passports as well. So with that fake token, we can brute force the pet pin on the WooKey, because there is no limit anymore on the number of trials it can do. And once we got the pet pin, we can go back to the original token, put it in the WooKey, and unlock the pet name. So we managed to bypass the first layer of authentication of the WooKey by that way. Okay, but to brute force the pin, we need some automation, and the keypad gets randomized at each boot, you remember. So the idea is to sniff the SPI command sent to the screen to reconstruct the keypad layout. We don't need a graphical reconstruction, and we just quickly fingerprint the sprites with some checksum to know which keys are displayed. Then we inject fake pressures from the touchscreen. For that, we hijack the touchscreen IRQ. It's a line that tells to the WooKey that there is some input, someone is pressing the touchscreen. And then the WooKey tries to sample the position of the touchscreen, because it's a SPI bus. So the touchscreen cannot just send data like that. It's up to the WooKey to interrogate the touchscreen. So the WooKey is alerted via the IRQ line, and then it samples the touchscreen to get some positions. So that's at that moment we send fake positions in response to the SPI commands on the WooKey. And finally, we need to keep an eye also on the smart card communication to see if the WooKey tries to mount a secure channel. If it's tried to mount it, that means the pin is correct. So what we need, the fake token with the extracted LK, a simple microcontroller. Here we use a Teensy with some Arduino code, but anything else would do it. A logic analyzer, it's not really part of the setup, but that's pretty useful to debug what's going on. And then we need to hook some wires on the SPI bus. So here you see we got some micro solders on the SPI lines and the power supply, the ground, the chip select. And then we need also to hijack the IRQ line. So we don't want anymore the IRQ that comes from the real touchscreen. So we cut the line somewhere here and we hook somewhere closer to the microcontroller. But that setup didn't work very well because wrong pins were typed on the touchscreen, or at least it received not the pin that we were intended to type on the screen. So we had to investigate that a bit further. And that's where the logic analyzer is useful, by the way. So actually there are a couple of bugs in the WooKey implementation of the touchscreen driver. One thing is the chip select is always active. So the chip select is the CS line you get here. And you can see that line is flat, and when it goes to ground, that means it's active. So it's active all the time. And one of the consequences is that the touchscreen is still active even when the SPI is used more for screen activity, because the screen and the touchscreen share the same bus. And the effect you see is that there is some funky stuff going on the IRQ line of the touchscreen, where nothing should happen actually over there. But that's fine. The WooKey is still working by chance. It doesn't perturb too much the operations. But that's the first issue. The second problem is bigger. Is that the routine to sample and average a position goes on even if the finger is released from the touchscreen. So here we have the IRQ line of the touchscreen that tells if we are pressing the screen, and we see it goes low all the time, so that means there is some pressure. And then here the pressure is released. What you see there is touchscreen activity when it gets interrogated. And indeed, the issue is that here on the first line, these are the commands sent by the controller and the response of the touchscreen that gives the position. So the controller is sampling the position several times to make some average and remove some noise. But the problem is that even when the pressure is released, the MCU is still sampling the touchscreen. But then the response it gets is zeros. So of course, if you make an average of these positions plus zeros, then you get a wrong position, which is shifted too much to the left. So the solution to avoid that problem is to take that into account when we fake the position, to be sure to respect the same cycle of the 16 measures. So we drive the IRQ exactly for 16 cycles of the sampling command, and we make sure that we reply 16 times with the exact same position. So at the end, we get something which is even more reliable by hand, because that bug appears indeed when you just use the WooKey touchscreen by your hand. Sometimes it types on the wrong pin. When you know that it can erase stuff when it detects too much errors, that can be really a big problem on that device. So here you see the boot sequence and the injection of the pen pin on the randomized keyboard. Here we type the pen, and then it will display the pet name. It takes a bit of time to appear, but it will be very quick. Yeah, here pin OK, whoopee, that's the pit name. pet name, and then it types the user pin, because here this is the demo board, so we have access to both pin, and we can show you how the final display is. At this point, secure master edge is mounted on the PC. So you see all this sequence is still rather slow. It takes about 15 seconds to boot up to the validation of the pet pin. So brute forcing that pet pin is quite slow. So after testing the setup on the demo board, we try on the closed sample for which we don't know the pins. And in about 15 hours, we managed to break the pet pin on the closed sample. Thanks to the recovered pin, we could discover the pet name by swapping the card and putting the real authentication card on the WooKey. So the first layer of authentication of the WooKey was bypassed, which opened potentially the door for phishing attacks by presenting a fake WooKey to the user with a correct pet name. So he will trust the fake WooKey and type the user pin. And if you put, for example, a radio to exfiltrate the pin in real time, even if he realizes that he cannot mount his data, you can then decrypt the stolen WooKey content. Now a few words on electromagnetic faults. The idea here is to inject an electromagnetic pulse that will perturb the MCU, inject a fault in execution, like skipping execution, an instruction, sorry. Typically, such attack is done in two phases. First, a characterization of the target processor by using open sample, where you can run some sample code to observe easily if a fault is injected or not. Typically, we put a loop counter, so we can inject at any moment, and if we see that the result of the counter is wrong, we know we managed to inject a fault. During that phase, we try to find good parameters, like how much voltage to inject. It's about 300, 400 volts. With which duration, where to put a little coin on top of the chip. Then we can try on the real target. Here we tried on the loader of the WooKey, where it checked the integrity of the firmware before executing the firmware. And we simplify a bit the target. We make sure it to disable the countermeasures, like it won't erase itself when it detects an attack. And we blink some LED at the end, just rather than running the full firmware. The main constituents are framework script that will coordinate all the hardware, where we will have something to inject high voltage pulses. Here I use a chip shouter, which is a bit costly, but you can probably do something by yourself for much cheaper. You just need a capacitor bank and a MOSFET. The advantage here, it's quite safe to use, because if you do by yourself something that handles 400 volts, you have to be very careful what you're doing. You need something to trigger it with a configurable delay. There is one in the chip shouter, but we wrote our own trigger in a small FPGA that you see here at the bottom. It's an ICE40 if you know it, to get better precision in the timing and in the pulse length. You need some XYZ table to move around the little coil on top of the chip. So here my XYZ table was just my 3D printer. But you can do that also on small CNC, for example. It's a bit easier. And you need the script to talk to the target and to reset it. So we have some control here made for the target. And you need to be able to reset the target, but because it will probably crash pretty often when you try to inject faults. And the script does also some cartography and automatic acquisition by varying parameters we've seen before. Here is an example of cartography. You see there the different parameters that were used, and then we try to scan all the chip surface for a given height. And we can use some colors to see quickly what happens. When it's green, it means normal behavior, nothing bad happened. Here in the blue, the target was not responsive, so we had to reboot it. Here in purple, it rebooted itself. So that means also that all cases that you have to handle in your script. And the more interesting parts are here in yellow and in orange, is when only a few number of instructions were skipped. So in the yellow, you see the number, that means there is only one instruction skip here, two instructions skip here. And with this cartography, you can see, for example, that maybe that area is pretty interesting because we don't have much crash, but we have small instruction skips. So we can try then the second phase only on this area, for example. So after the categorization, to find a good spot and good voltage parameter, we move to the target. Here, the loader of the WooKey that checked the integrity of the firmware before launching it. And here are some results we got on the loader. We got a first integrity bypass after about 5,000 attempts. And after some fine-tuning, we got a success rate of about once every 14 attempts. Maybe it's possible to get better, but it needs time to explore all the parameters of an EM fault injection. But remember, on the real WooKey, there is a really defense in depth. As soon as the loader fails to check the integrity of the firmware, it erases everything. So still hard to really get a full execution path, attack path on the WooKey. So here it was just to test and see the feasibility of the fault injection, where we disable these countermeasures. By the way, we got also some other funny and less funny results. For the funny one, we got portions of the firmware leaking on the debug UART. That was not foreseen, but it happens. And that's really, with fault injection, like anything can happen really. Hopefully the UART is disabled in production. It's only on debug mode. But maybe you can do something similar on the USB descriptors, for example. For the less funny part, we also try to defeat the STM32 LDP2 protection. That's a protection, physical protection that forbids you to dump the content of the firmware over JTAG. And when we try to defeat it, we break the demo board after a while. So this is a gentle reminder I wanted to share with you that when I say anything can happen, it means including destroying the target. So always be very careful when playing with fault injection. I hope you enjoyed these stories. Here are my conclusions. Hardware attacks are fun to do. They are much more affordable than some may think. No need for big lab to start poking around. You've seen it with these stories. Never assume that you have in front of you is robust. Try by yourself. We've seen here issues on certified Java cards. We've seen crypto protocols weaker than foreseen. So it's always worth to challenge the things you see. Even if it fails, at least you can learn something in the process. And finally, if you got a test for the topic, I warmly welcome you to have a look at 2 books published very recently, like 1 or 2 months ago. The first one is a nice introduction to the topic, and the second one gives it goes deeper in fault injection and side channel, but still always in a style hacking at home without big equipment. Thank you, and I'm hearing your questions.
Okay, thank you, Phil. I think we got a number of questions. You want to start first, Sean?
Yeah, sure. Thank you very much for the presentation. Just a quick question about the methodology. Did you try to use power glitch in order to have a better reproducibility? Because EM is a bit difficult to get high reproducibility rate.
You can hear me, I hope.
Yes.
Yes, perfect. Power, you mean voltage glitch? It was not part of our plan. As I explained, we had a huge plan to attack the WooKey, and each CESTI did part of it and got a part attributed. And in our part, it was only EM. But if I remember well, last year, Sinek presented his result on the voltage glitch on the WooKey.
Okay, thank you.
Okay, thank you, Phil. I think you had a question on the live about the PTS update and when was it being done before verification or not. Would you mind repeating your answer for the rest of the audience who were not following that exchange, please?
Yeah, so there was a question if the pin counter check is updated correctly before doing the verification. Otherwise, you could like try to verify the pin and tear off the card very quickly before it updates the counter check. Again, this was not something that was on our plan, and we had already quite a large plan to do in the CSPN days that are foreseen. So that's not something we looked at. Not that we didn't want, but yeah, we have to limit ourselves to already quite a number of things. But
Okay.
I hope, I assume that this correct, this one. I mean, the bug we found is maybe because it was something which was not really on the checklist for the certification labs when they attribute an EL6+, but I hope that on the EL6+ checklist, at least the check for tier of attacks.
We hope so. We've got last question from Pascal.
Yeah, thanks for the talk. And my question is, how many hours does it take to do solving this challenge? Yeah.
Here it was 3 items of our plan. The plan was much longer, and it was filling a full CSPN, which is 25 days plus 10 days when you have some crypto in it, so 35 days. But yeah, that's a regular CSPN, including reporting, including looking at aspects which are not just finding the vulnerabilities. So just for these items, well, the first one, the timing attacks, that's something you can do in a day or in an afternoon. It's very quick. The one with the instrumentation, you saw we had some difficulties to work around the bugs, finding what were the issues with the WooKey. So that one took probably like 4 days to set up. And the last one, the test bench. Actually, we didn't have yet a test bench when we started. So most of the time was about setting up the things, setting up and writing script and writing cartography script. Then running the attack, it's about, I don't know, 1 day to set up the stuff and then a couple of days to run the tests.
Okay, thank you very much.